Hello and welcome to day 18 of Advent of Code 2024. This problem is called RAM run. So you and historians look a lot more pixelated than you remember. So you're inside the computer at the North Pole. just as you're about to check out your surrounding, program runs up to you. This region of memory isn't safe. The user misunderstood what the push down automation is, and their algorithm is pushing whole bytes down on top of us. Run! And the algorithm is fast. It's going to cause a byte to fall into your memory space once every nanosecond. Fortunately, you're faster. And by quickly scanning the algorithm, you create a list which bytes will fall. Your puzzle input. In the order they land in your memory space. Your memory space is a two-dimensional grid with coordinates that range from 0 to 70 both horizontally and vertically. However, for the sake of example, suppose you're on a familiar or on a smaller grid with coordinates that range from 0 to 6 and the following list of incoming bytes positions. Yeah, so we get this kind of input list, and let's continue here. So each byte position is given an XY coordinate, where X is the distance from the left edge of the memory space and Y is the distance from the top edge of the memory space. You and historians are currently on the top left corner of the memory space at 0.0 and need to reach the exit in the bottom right corner at 70 in your memory space, but at 6 in the example. You need to simulate the falling bytes to plan out where it will be safe to run. For now, simulate just the first few bytes falling into your memory space. As bytes fall into your memory space, then make the coordinates corrupted. So corrupted memory coordinates cannot be entered by you or the historians. So you'll need to plan your route carefully. You also cannot leave the boundaries of the memory space. Your only hope is to reach the exit. So in this example, if you were to draw the memory space of the first 12 bytes have fallen using dots for safe and pound signs for the corrupted ones, it would look like this. So you can take steps up, down, left, and right, and after just 12 bytes have corrupted locations in your memory space, the shortest path from the top left corner to the exit would take 22 steps. Yeah. So this is again kind of shortest path problem, and we get this list of coordinates for the kind of corrupted bytes, which will also be the coordinates for where there is actually we can look at them as a wall. So first one I read is I thought that that these would kind of move along as we move, but they will just end up here. So for the example, we will take 12 of these bytes. So we will not take all of them. So we will take 12 of these bytes and kind of put them in as walls in our example, but we will not do it exactly like that, maybe actually. But yeah. So without further ado, let's jump into the code. So this is, as I said before, is a pathfinding problem. I can already have prepared some code here to not waste time doing this. So we will kind of read in the input list. Yeah, let's just grab this test input first. Yeah. So we will not run the real input. We'll obviously run the test input. So the test input here is the corrupted bytes. even if the examples taught they refer to them as xy coordinates, I think it's much easier to think of them as row and column, as this is just 2D space. So in the input I need to put the second one first and the first one last, because they always start with the x, and the x is the column. So yeah, you get it. And yeah, so we have our list of corrupted bytes here, and we will do our find path so we will have a method for this. So in this as we said, this is a pretty easy breadth first or Dijkstra. Well, I'm actually going to use a priority queue, so it will be more of a Dijkstra solution, but not in that sense, because the only priority we will use is the number of steps. So yeah, so let's begin here. We will have our starting position, which will be our row and column, which will be our start, which we will set to 0.0. Yeah, right. And also one more thing, we will kind of as we said here, the size. So we define a size. So it will be as it will be the same with the height. We don't have to define the rows and columns as usually, but we can only refer to it as a size. So the size will be 6. For our test example, and bytes to check will be 12 for our test example. So this is just so you can switch back and forth from the input and to the test input. Yeah. So we have a walk queue, which will be our new priority queue, which will have our int row, int col, int steps. So int steps, and it will also be the t priority will also be an integer. So as normally we actually want to keep track of the steps. I also have them in as our t element as well, or t priority element. So we will also have a scene, which will be our new, normally this will be a hash set. This will only contain the row and col, and we start by queuing up that first step. So it will be kind of start row, start call, and 0 for 0 steps, and 0 as initial, and we will also add it to our scene. We will add start. Yeah, so we're set here. As I said before I added it, what we are going to look for here is the minimum number of steps. So as usual, we have a while loops where the which will run until the count from the queue will be empty, and so pretty straightforward in this example, as I said. So we will queue our current row, current column, and steps from the queue, and then we will start looking around. So we will do for each. So we will do VRDC in this type of structure here. So we will have up, we will have left, right, we will have down, and we will have left. Yeah, that's it. Yeah. So from these we will kind of we'll have our new row, which will be our current row plus our direction row, and our new column, which will be our current column plus direction column. And also we'll just pull this in. We have kind of a method here. So we have a local method that says that is in corrupted memory. You will take in our position and also number of bytes to check. So we will take our corrupted bytes, pick out the number to check, and then just check if this position is in one of those places, then we're into a ball. So if is in corrupted memory, well, I actually see I've misspelled this. Yeah, I need to fix that in my real code as well. So if this new row, new column is in that corrupted memory, also we tell them how many bytes to check, then we just continue. If we are in bounds of the grid, we will say that if new row is less than 0, or new column is less than 0, or new row is greater than size, or new column is greater than size. We will also continue. This is as we said, that size is, so it's inclusive, so that if we have written the size as 7 in this sense, we would have kind of wanted to have this as greater than, but we would probably be in it. So this is the inclusive size, yeah. So we will also do we will also check if it's in the scene. We will also continue. Yeah. Also, if our new row is equal to the size, and our new column is it. So if we basically if we are at our end position, which will be in the bottom right corner of the grid, we will set our min steps to the steps, and we will break. Yeah. So the only thing left is to add our position to the queue, to the scene, and add it to the queue as well. The queue. So we will have like nr nc the steps +1 and steps +1. This will be it actually. So the minimum steps within this grid take after just 12 bytes has fallen will be yeah, we need to kind of we don't have it there, so we just find path with our corrupted bytes, our size and bytes. Yeah. So when in this example we should have it should be 22. No, actually not. Oh, something is wrong here. What could it be? Something is wrong here. It should not be 23, it should be 22, right? 22 steps. Let me just some reason my code is well, it's working for my real example but not for the test example. Yeah, really strange. It should be the other way around, but just to show you with my real example, with my real input, just to kind of prove that this actually solves it. But yeah, so if we change to the real size and to the 1024 bytes, we will have we should have the oh, sorry, I'm running the wrong project here. Yeah, so we have our 432, and this was my answer for part 1. Sorry about it should be 22. I don't know why my code doesn't get 22, but and I know when I did solve it I got 22, but for some reason I did some changes, but I at least get my real answer, so I'm confident that this is the correct solution, of course. So So let's move on here to part 2 then. Yeah, so part 2 here is also pretty easy. We can just read the text here. So the historians aren't as used to moving around in this pixelated universe as you are. You're afraid they're not going to be fast enough to make it to the exit before the path is completely blocked. So to determine how fast everyone needs to go, you need to determine the first byte that will cut off the path to the exit. So in the above example, after the byte 1.1 falls, there is still a path to the exit. So basically what they're saying is that they want to see how far in the byte count they can go, and you need to stop at the first byte that will make the end path not reachable. And for the example here, we want to have 6.1, and I actually saw that, well, using my test, using my code, I get that value. So my code actually works for the test input for the part 2, but for some reason not working for part 1. I don't know, and I don't know what happened to it, but something happened. But we can continue with the real input anyway. So we will. So in this case, I will have 56.27, and that is kind of the XY. So in our code, we have to kind of reverse it. You have to think it's row 27, column 56. Yes. So we go back to our code here. We will actually just do some smaller modifications to this. So instead of this, we can actually remove this line here now, because we're going to check something else here. So our find path method will now return kind of a tuple with min steps. Well, actually, we don't actually need the min steps for this part 2, but this is how I did it in my real example, just because I wanted to use the same method for part 1 and part 2. But just for the sake of example here, I've added it here. So we also want to change the return, of course, and this will kind of, so what this will do here is that if this min steps is still 0, if it's 0, then this byte count will make it unreachable, basically. And then it's just a matter of doing a kind of a binary search for this. So you could actually just do a normal loop, increase the bytes as you go. You obviously need to start at the last byte that you got from. So let's say bytes. If bytes was 24. Then or 1024, as in our first example, we could start looking at 1025 and up. And in the real example there are over 3000 bytes, but we don't actually need that anymore. So what we will do, we will define low, but I will do this a bit differently. This is much faster. So we will have a high, which will be our corrupted bytes count. We will also do while low is less than high. and then our minimum will be equal to our low plus high divided by 2. So this is kind of splitting up. So we have a low part and a high part. We're just going to find out where we are in that. So we check this path. So we say result equals find path, which will be our corrupted bytes. We'll send in the size and which will be our min plus 1, and if our result is possible, we will set the low equals min plus 1. So now then we will increase our low, and if it's not possible anymore, we will set our high to our min value, and then our kind of part 2 answer would be like follows. So we have a part 2 which will be our